Now, kind of where we left off is the past couple of chapters I've been saying that light is definitely a wave, definitely a wave, definitely a wave. However, in this particular chapter, I'm saying wave is definitely a particle, or light is definitely a particle, and definitely a particle. Now, this is actually going to lead us to this creature called wave-particle duality. And what this means is light is sometimes going to behave like a wave, and it's sometimes going to behave like a particle. And in general, what we can say is light is going to behave like a particle when it is either emitted or absorbed. So if it is absorbed or emitted. When light goes from one place to the other, then it's going to behave like a wave. So as a wave travels, then it's going to exhibit wave-like behaviors. So I haven't really been lying to you, but what's going on is light is sometimes going to behave like a wave, and it's sometimes going to behave like a particle. So light is both a wave and a particle in that sense. So let's just kind of really quickly talk about what happens when we take a picture. Well, when we take a picture, we're going to have some light that's incident upon some film, if you're old school, or on some CCD array that's inside of your phone. Now, if you've ever taken a picture in dark light, it looks kind of grainy, doesn't it? Well, what happens when we build up a picture? Well, we can work our way from A to B to C to D to E to F and say that this is going to be the interactions of photons with our CCD array. So light is exhibiting its particle-like behavior as we take our picture because the light is being absorbed. Not a lot of light, we're going to see something that's really grainy. A little bit better light, going to look like this. Take a longer time exposure, and maybe you're going to see this. This image is actually being built up a photon at a time. So it's going to look like this, and then this, and like this. And at the end of the day, we're going to have our picture. So maybe I'm not telling you anything that you don't already know. If you don't have a lot of photons, we're not going to have a very good picture. The same is actually true for this thing called the double slit experiment. Here we have a light source. Here light is being emitted. In this case right over here, we're going to say that light is behaving like a particle. We're having some transitions, and the energy level is going to be related to the frequency. Light right here is being transmitted. So as it goes through this portion right over here, it's going to act like a wave. It's going to go through this. It's going to continue to act like a wave. It can interfere with one another. Light's acting like a wave. As soon as it hits the film, then it's going to act like a particle. So right over here, it's going to act like a particle again. So we're kind of seeing the wave nature and the particle nature as we go back to this double slit experiment. Bear in mind that these bright spots are being built up a photon at a time, so it looks kind of dodgy here towards the edges. That's more or less what's going on with this guy. If we were to just let a few photons sneak by, then it's going to look a whole awful lot like that picture does. If we only let a couple of photons in, we're going to see a smear that kind of looks like this. If we waited a little bit longer, then we're going to start to see the bright, dark pattern that we kind of expect to see. And if we were to expose this film for a long time, then we're going to see this one, and longer still, and we're going to see the pattern that I showed you a couple of chapters ago. If we were to go ahead and cover up one of the two slits in this double slit experiment, then we're just going to see a diffraction pattern. And somehow the light knows this. This is kind of the wave-like nature of light. What we're going to have is we're going to have the wave-like nature of light as it goes through the single slit, and we're going to get the pattern that's going to look like a single slit diffraction pattern. We're going to have one really bright band, and then we're going to have a dark band on either side, and then we're going to have a bright band, dark band, and so on and so forth. Bear in mind that when it hits the photographic film, we're seeing the particle nature of light, and so this guy is going to build up one photon at a time, so 1, 1, 1, 1, 1, 1. You wait long enough, and you're going to get a nice fuzzy edge right here. Now, this just kind of says in text what I said on the previous one, but it is worth repeating. When light is emitted, it's going to behave like a particle. However, each photon, each chunk of light, is going to have wave-like properties as well. It's going to behave like a particle when it's emitted and when it's absorbed, so from the laser and on the screen. and it's going to behave like a wave as it goes through the single slit or the double slit, because it's going to be able to constructively or destructively interfere with the other waves. Now, you may be saying to yourself, well, how come light can have wave-like nature and a particle-like nature? I mean, light is a wave after all. Well, it turns out that everything is going to exhibit a particle-like nature and a wave-like nature. Now, most objects, like you and me, we're too big to exhibit our wave-like nature. This fellow by the name of Louis de Broglie came along, and he actually related the wavelength to Planck's constant and the momentum of an object. I'm going to go ahead and shorthand this. Wavelength is equal to Planck's constant divided by momentum, and if you remember, the momentum of an object is actually going to be its mass multiplied by velocity. That's a concept from Physics 101, but yeah, hopefully you remember that. And the thing is objects like you or I, we are very, very, very massive, so our momentum is relatively large. What this means is we're dividing Planck's constant by a big number, and Planck's constant is a small number. It's 10 to the minus 34. Objects like you or me, our wavelength is going to be very, very, very small because we're dividing a small number by a big number. So objects like us, our wave-like nature is going to have a wavelength that's so small that we really can't observe it. And it would be kind of silly if my wave-like nature came out and I diffracted when I went through openings. However, if we were to think about electrons aren't very massive. They're going to have a mass of 10 to the minus 31 kilograms. They're actually small enough that we can actually see their particle-like nature and their wave-like nature. Electrons are going to diffract as they go through as they go through openings, and electrons can interfere with each other. Bear in mind that every particle is going to exhibit wave-like nature and particle-like nature, and if it's small enough, we can see it. Now, electrons are far more massive than photons are, so their wavelength is actually going to be shorter than photons, and it turns out we can actually resolve stuff far better with things like electron microscopes because of this. I'm going to go ahead and use this equation in the next chapter and calculate what the wavelength is for an electron and for a baseball, I think, and I'll save that for next time. Now, this picture right here is going to show the diffraction of both light and electrons going through some barrier. And what we can see right over here is here we have some beams of light and it's been diffracted off of some object. And here we have some electrons that have been diffracted off of some object. Bear in mind that the wavelength of the electrons are going to be smaller than that of the photons, or of the light, and so we're going to see a far more granular pattern here. As I mentioned, applications of treating electrons as waves is going to be electron microscopes. Using the wave nature of electrons, we can bombard things like this little insect right here with electrons, or this mosquito, and because the wavelength of the electrons is very, very, very small, we can actually resolve things far better than we can with visible light. Visible light is going to have a relatively large wavelength, and that's going to limit our ability to resolve things. Just a quick little check your neighbor thing. When I talk about these waves, which are actually called de Broglie waves, we're talking about the wave-like nature of particles. Now, the last thing I want to finish off with this chapter, and this is kind of taking a jump, but it is related to quantum mechanics, and this is related to the something called the uncertainty principle, or the Heisenberg uncertainty principle. Now, whenever we try to measure something that's really, really, really small, something that's really tiny, it turns out that we cannot do so perfectly. Trying to observe something like an electron is going to probe the electron, and there's going to be some uncertainty in our measurement. It turns out that we cannot know its position perfectly, or we can't know its velocity or its momentum perfectly. So there's some limit in our ability to be able to measure things. There was a German physicist by the name of Heisenberg, and he's the one that kind of came up with an equation to describe this. And what he did was he said that there's going to be some basic uncertainty in our momentum. And again, momentum is mass multiplied by velocity, and this little delta means the uncertainty. If we were to take that and multiply it by the uncertainty in the position, then he said that this has to be larger than this thing called h bar. And all h bar is going to be Planck's constant divided by 2 pi. Now, this looks kind of abstract, so let's see if we can boil it down and make it a little bit simpler. Suppose I were to make some measurement, and I made this really good measurement of the position of an object. So as my knowledge of the position of the object goes up, the problem is my knowledge of the speed of the object has to go down. The product of the momentum, the mass times the velocity, multiplied by the position, has to be larger or equal to this thing called Planck's constant over 2 pi. On the opposite side, suppose I knew my speed of an electron very well. I wouldn't have a very good knowledge of where it is. Now, this just kind of says in text what I said in the last one. The delta really kind of says uncertainty, and it's uncertainty in momentum. This is uncertainty in position. And again, the product of the two of these has to be larger than some number. It's a small number, but it's a number all the same. And bear in mind, this is only going to be applicable when we're talking about things that are really small, like electrons or atoms or stuff like that. Once in a while, what we can do is we can actually write this in the language of energy and time, and it turns out the uncertainty in the energy multiplied by the uncertainty in the time also has to be larger than this creature called h bar, which is again going to be h over 2 pi. I'm not going to belabor this point because I don't really do a whole awful lot with it. Now, I don't want you to write in your lab write-ups that the uncertainty in this lab is due to Heisenberg's uncertainty principle. Bear in mind that this is only going to apply to quantum mechanics, or in other words, is only going to apply to things that are very small, like atoms and electrons and stuff like that. These are microscopic measurements. It does not apply to macroscopic laboratory measurements. We are not in any way trying to hide any secrets from you, and please don't think that all of science is basically uncertainty, or all science is basically uncertainty. Uncertain. Most of the stuff that we're talking about is really big, and we know this stuff quite well. This is only going to apply to things that are small. Now that we've introduced a whole lot of uncertainty to this particular chapter, I've said sometimes light is a wave, sometimes it's a particle, sometimes we don't know where something is or how fast it is moving. I want to kind of finish on a happier note. I actually want to talk about how everything is really kind of complementary. And this fellow by the name of Niels Bohr, who did lots of work on the atom, we talk about the Bohr model of the atom in the next chapter, he actually chose this symbol called the yin and the yang to represent the wave-particle nature of light. So we could say that this guy right here might be the wave nature of light, and this guy right over here might be the particle nature of light. These two guys are going to complement each other, and complement each other quite well. The same is true for the yin and the yang and waves and particles. Sometimes it's nice to be able to describe light like a wave. Sometimes it's nice to describe wave or light like a particle. In fact, we have to describe it as a wave and a particle sometimes. So these guys, while it seems like it's a little bit strange in some ways, they actually complement each other quite well.